evening and a warm welcome to the CIVI-NAR series organized by the Civil Engineering Student Technical Club of NIT Rourkela. It is more than just a club. The club aims to provide a platform for the student to think, reflect, and wonder about the phenomena involved in civil engineering. Now let's have a glance on a club through a short clip. I am delighted to introduce you to the executive body members of CEST on board, Mr. Satyan Raj, President of CEST Club, Mr. Aditya Chandra, Content Head of CEST Club. Today, we are thrilled to welcome you to CIVI-NAR, a platform where the world of civil engineering, innovation, and knowledge converge. It's a dynamic platform where the entire civil engineering community come together. As we carry forward our legacy, today's discussion delves into the topic the potential of magnesium-based cement and concrete to curb CO2 emission. Before we embark on this enlightening journey, I would like to extend a warm welcome to our CEST Club faculty advisor, Dr. Subhajit Mandal, who serves as an associate professor in the Department of Civil Engineering at NIT Rourkela. Moving forward, we will be hearing from Professor Paivo Kinnunen, who is an associate professor in the University of Oulu, expert in Fibre and Particle Engineering Research Unit. He graduated from the University of Mission with PhD in Applied Physics in 2012. Now I invite President of such club for his warm greetings.
Good evening, everyone. This is Satyan Raj, President of the CEST Club. It is with great pleasure and immense enthusiasm that I extend a warm welcome to all of you to the CIVI-NAR series organized by the CEST Club of NIT Rourkela. Today, we are honored to have Professor Paivo Kinnunen with us as our distinguished guest lecturer, and we are thrilled to have Dr. Shubhajit Mandal, the faculty advisor of our esteemed club, gracing this event. The CIVI-NAR series is a platform where knowledge, expertise, and ideas converge, and we are delighted to see such a wonderful turnout. Your presence here today reflects your dedication to learning and your eagerness to engage in meaningful discussion. Professor Paivo, we are truly privileged to have you share your wealth of knowledge and experience with us. Your insights are sure to inspire and enlighten us, and we eagerly anticipate your lecture. To our esteemed audience, thank you for joining us. Your active participation and curiosity drive the success of the CIVI-NAR series, and we look forward to your valuable contributions during the discussion. Let us make the most of this gathering and embrace the opportunity to learn from one another. Once again, a warm welcome to all of you. Thank you for joining us.
Now I kindly request Subhajit Mandal sir to extend his warm greeting to Professor Paivo Kinnunen.
Hello, Professor. How are you?
Hello. Nice to see you. Very nice.
Yes. How that Sri Nandan is working there?
What is that?
Sri Nandan, he was working here earlier, and now he's joined your university.
That's right. Yes, he just joined recently. Yes, very well.
Okay, good. So very welcome to the CEST club. This club is basically run by the student, and main interest of this club is to encourage the student for the research. In our civil engineering society, we observe that many students after doing their undergraduate, they directly going to job. So my interest was to encourage them to the research. So we invite all the lecturers all over the world so that they can gain the knowledge and have interaction with all the international faculty. Okay, so I welcome you to this CES club. So please, it's your time now. Thank you.
Thank you. Thank you for the kind introduction, Priya, and also very nice to meet you all. Let me share my screen.
Now, without further delay, let's get started. I kindly request Professor Paivo Kinnunen to continue with the presentation.
Sounds good. Can you see my screen now? I believe so.
Yes, it's coming.
Okay,
Yeah, we can.
great. So I will give you a brief introduction into the topic of magnesium-based cements, and especially their potential to curb the CO2 emissions. But first, I'll just introduce myself shortly and our research group. So I'm working in this Fibre and Particle Engineering research unit, which is at the University of Oulu. Here you can see on the map where we're located. So it's actually a quite northern part of Finland. And we are, the whole group is about 60 people, and it consists of 3 subgroups. So there's this inorganic binders research group, which is led by Professor Mirja Ellikainen, and where my group is also. So my group is this magnesium-based materials and systems. And then there's also cellulose research group that's led by Professor Henrik Liimatainen. And this is actually a picture from earlier this year. So we were ordered by the city of Oulu to produce these uh, sustainable concrete letters at the city center. So we're quite pleased at the end results. Okay, so but without further, let's deep into the discussion. So the reason, of course, why this topic is important is the search for a more sustainable design of a society. How do we arrange our lives in such a way that we can actually live sustainably, meaning that we can actually exist for more than a brief moment on this planet. So, and recently you may have seen this planetary boundaries framework. So this was originally published perhaps already 10 years ago, but it has been updated recently in September. And here you can, it was actually quite substantially updated. But there, so here we have it's basically 9 different dimensions that are considered, and they have this safe operating space that's been um, uh, sort of um, uh, that is known so far. And here you can see that the CO2 concentration, which is one of the aspects, is quite far into the zone of increasing risk. So it's not quite into the highest risk zone, but it's right there at the edge of it. And so that is the main reason why we are here considering the CO2 emissions. Of course, the cement industry is globally responsible for something like 8% of the global anthropogenic CO2 emissions, and so that is why cement and concrete are important places to look at for improvements. And also, what will become clear is that not only is it high sort of outputting a lot of CO2, but it's also the place where we can actually store a lot of CO2 for the reason that concrete is the most used material on the planet. So if we're looking at, if we're looking for places where we can store carbon dioxide um, and utilize it, that would be the application, and that's what I will be talking about later as well. But that said, I think it's also important to also keep in mind that this is not the only planetary boundary that we're uh, hitting up against. So we should always consider all of the other boundaries as well, so that we don't actually accidentally create a technology that will end up in problems, especially given the fact that most of the, or if not all of the problems that we're facing are um, unintended side effects of previously sustainable, something that was considered sustainable previously. So with that in mind, I think we should be really careful about thinking what are the unintended side effects of the technologies that we invent and take into use. So here's the CO2 emissions for the past couple hundred years, and this of course reflects the global increase in technology use, and it has been exponentially. It's so-called hockey stick exponential curve, and it's been going upwards recently, and so that is the issue that we're looking at, and and so what to do about it? So here's the sort of natural. There's you can say that there's slow and fast carbon cycles. So the slow carbon cycle is this gray arrow that goes from the atmosphere to the soil to sediments and then to basically minerals that then enter back into the atmosphere. Um, but I mean, they degrade and the CO2 enters back into the atmosphere. But that loop is a slow cycle, which it takes hundreds of millions of years. So it's a really slow moving cycle. And let's see, let me hide this so you can have better visibility. So basically, then we have another one, which is called the fast cycle, which is the carbon dioxide going from the biosphere to the atmosphere and to the ocean and so forth. And so there are two basic issues. Two of the reasons that I would highlight here that are the reason behind the high atmospheric carbon dioxide levels, which is that we have basically short-circuited the slow cycle. So what we're doing is we're taking some of the minerals, such as calcium carbonate, and turning it into calcium silicate, which is the cement production process. And as a result, we produce by weight about the same amount of CO2 emissions. So we're basically taking this slow cycle and short-circuiting it and turning the CO2 back into the atmosphere. And then the other one would, of course, be the fossil fuels, and that's about the same story, where we take the fossil energy and turn it to the atmosphere. So with that in mind, I think as a design principle, how should we then sort of counteract that? I think it's a useful way to think about it in a way that we need to reverse that. So we need to short circuit it as well from here. So we need to take CO2 from the atmosphere or from the processes and store it into minerals that are stable for hundreds of millions of years. So we're basically would need to counterbalance the earlier short circuit by another one. Okay, and so now we'll sort of go into the technical details later. What does that mean? But first, this is the sort of local incentive here. So in EU we have this carbon tax, and and it varies by the country. So I'm sitting in Finland, and here it is about 76 euros per ton. And in addition to that, the companies also have to pay a sort of carbon permit, which is about the same amount. So this is the local incentive, and the local incentive basically for the companies to change their processes. And so what are the different um, ways? So maybe I'll first go a bit into the nomenclature. So CCS is carbon capture and storage, carbon capture and utilization, and then CCUS is carbon capture, utilization, and storage. So basically what we have here is we have industrial emissions. We can do this industrial capture, which is the second C, and then we can either use it directly for enhanced oil recovery, which is called carbon capture and utilization. You can see up here is the basically the what is called, so CCU here, and then you can do underground storage, which would then be CCS. But then we can also convert that to carbonates and then basically make different products out of that. And so here, what we're looking at is something mineral carbonation or mineralization, and they're concretes and cements. So that's a viable carbon capture and utilization pathway. But so the legislation, at least here in EU, is not clear about this yet, but that can actually also be considered carbon capture and storage. So you could use that as carbonates, and then if it is long, if the time that the product is in use or stable on the crust, that could be considered also storage. A little bit also on the same vein here. So here on the y-axis you have the different source of the carbon. So if you have air carbon and then you make a short-lived product out of that, that's called carbon recycling. If you make a long-lived or geological storage, it's called carbon removal. Also if it's bio process derived carbon, that's the same thing. But if you have a fossil carbon and you make short-lived product, it's not considered. But then if you make a long-lived product, you can call that emission reduction. Also, even if you store that, it's still just called emission reduction. So depending actually where the carbon is coming from, it has a like a different legislative framework that it fits under. And so here the product examples of the products could be something like fuels. Those are short-lived polymers, but then long-lived products could be concrete or mineralization, and then biochar, for example. Okay, so then let's dive a bit into carbon mineralization. It will become clear in a minute why that's relevant. So here, what we do first is carbon capture, either point source or direct air capture. We get the CO2. And then we also get industrial solid residues, or we can mine different minerals such as serpentine, olivine, or wollastonite. So those are magnesium-containing minerals. And what you can do then is so-called ex situ carbon mineralization. In situ mineralization would be something where you mineralize it inside, like underground. But ex situ means that you're taking it out of the ground and then do the mineralization. And then what you're producing basically is engineered magnesium carbonate or engineered calcium carbonate. And those can have different products, such as paper fillers, for example, for calcium carbonate and so forth, but also construction materials. And we're not going to go too much into the chemistry, just here to show that if you, for example, start from serpentine, you have magnesium silicate and some OH groups there. You take some carbon dioxide and you turn it into magnesite, magnesium carbonate, some silicon, some silicates, and some water. And that's actually exothermic process. So you also get some energy out of it as well. So that's carbon mineralization process, and different technologies that you can use for that. This is something that's sort of a very active area of research and active area of also different startups. You can see the different companies listed here on the left. This is maybe a couple of years old information already. So this is changing rapidly. But anyway, what I want to point out from here is that there are TRL ranging from 3 to 9. I would say 3 to 10 or 4 to 10 right now. These carbonate and carbstone, those are already in the market. So that would be TRL 10. TRL here meaning technology readiness level, where 1 is just an idea and 10 would be something that's already in the market. Um, so, so I want to point out here that there are already processes in the market. But another thing that's interesting here is that those that are the only one, let's say the other way, the only one that's based on magnesium is this green minerals carbonation of olivine, and that's TRL4 currently, I believe. And the rest are actually based on calcium. And so why that's important? Let's look into the next graph. So the reason why it's important, whether that's calcium or magnesium carbonates, is that if you start to look at the global emissions, so here this is a y-axis is the carbon emissions and storage potential of different materials, and this is a logarithmic scale. So, and this is millions of tons on a logarithmic scale. So first you can see that the cement industry's CO2 emissions are somewhere around 4 gigatons per year. Um, this right here. But then you have, if you look at the total all anthropogenic CO2 emissions, the emissions are about 40 or 50 gigatons per year. And so my let's say motivation for this work has more to do with the global CO2 emissions. So how do we actually um, um, what are the different possibilities in the construction, concrete and cement that could have like important input for the CO2 emissions globally. And so if that's our aim, we can compare this number of global emissions to the different industrial wastes. So here we have a different industrial wastes and the gray bars. And what we can realize is that there's actually between 100 and 1,000-fold difference between the amount of different industrial side streams or industrial wastes or their capacity to store carbon dioxide and the carbon dioxide emissions. So of course, it makes sense to use these waste materials, and they should be treated and should be used. That would be the first priority. But even if they were all used, that would not make a dent in the global CO2 emissions. So in that sense, what from the sort of carbon mineralization perspective, the minerals that are available in large enough quantities would be the bars above the highest line. So these are two different bars. So this is calcium and magnesium silicate rocks, and then seawater brine. And somewhat surprisingly, seawater brine is a really high. There's a high amount of magnesium available there, and it is something that's being produced more and more as a result of seawater desalination efforts. And another thing to point out here is that this calcium and magnesium silicate rocks is actually just magnesium silicate rocks. Calcium silicate rocks they do exist, but they're so rare that they don't they're not a feasible feedstock for carbon mineralization. So this is why the magnesium carbonation technologies specifically, and whether magnesium binders as well, are important topic, is because this magnesium exists on the earth as magnesium silicates, which is carbon-free feedstock. Unlike calcium, calcium exists as a calcium carbonate, and there, in order to utilize that, you always have that chemistry related CO2 emission there that you have to take into account. So that's the reason why I believe magnesium has a really high potential impact here. So what are the different sources of magnesium, and how do you tap into those? So here's some seawater processing. So but you basically have new technologies such as membraneless electrolyzers, and then you precipitate, you increase the basically you increase the pH, and then you precipitate and then filter out, and that would be brucite, so it's magnesium hydroxide. That's a solid mineral that can be separated out. And so this is one process, and then the other process would be sort of pH swing. So here, what you start from is a magnesium silicate rock. This is olivine, so there's magnesium, a little bit of iron, and silicate. And what you do there is you add hydrochloric acid, or it could also be sulfuric acid, to lower the pH, and then you slowly start increasing the pH, and then you recover. First, you recover silica, which does not dissolve there, so you can remove it right away. And then you increase the pH enough to get the magnesium hydroxide to precipitate, and then you can recycle the solution. And so this is a new, or let's say, developing method to um, tap into the magnesium resources, into the magnesium silicates. And here's just map of continental ultramafic rocks. This is really not how do you say, comprehensive. There's a lot of gaps here. Um, and one reason being that as because magnesium silicates have not been industrial feedstock in a large scale, so they have not been mapped so well, and so that being the main reason why it's the data is not available quite yet. Um, so how can you then marry these two? The like what are the how is this relevant to cement industry? So this is one way that is relevant, and I'll sort of blend it into in other ways. But this is maybe the how would you say, low hanging fruit in terms of the utilization potential. So this is published in Nature, I believe, maybe a year ago or 2 years ago. So this is the current process. So limestone mining, and then you have a conventional cement plant with plenty of CO2 emissions, and then you produce a cement mix. So what they have suggested here is you start mining. In this case, they could be olivine, and then you have a mineralization plant where you take in the CO2 emissions from the conventional cement plant, and then you make those magnesium carbonates, and those magnesium carbonates can then be stored in another mine site. And what you can do then with the silicates, because you're producing, or you're processing magnesium silicates, so your one side stream is actually really reactive silicates. So you can use those silicates as supplementary cementitious material, and then you can blend it into your conventional cement, and then therefore you're at the same time reducing the CO2 emissions of the cement, but you're also capturing the CO2 emissions that you're producing and storing those effectively. So this is um, one way that could be combined. And here you may notice that actually you're not using magnesium binders at all. You're just using the cement binder and supplementary cementitious silica. Um, and this approach, although it may be sort of easy to sort of start using, it has the sort of byproduct of having to store those minerals. And I think this is difficult, at least in Europe, to open new mines, so that you actually have to open new mine, and also have to open a new waste storage, or landfill for the waste material. So this is not perhaps environmentally so feasible, depending on the locations. So it would be better if we could actually use also these magnesium carbonates, or in the first place not produce these carbonates, these carbon dioxide emissions at all. So that's why we will then look further into the magnesia-based cements. Um, okay, so here's a figure. This is actually missing the citation. This was this year published review from the RILEM Technical Committee on magnesia-based cements. you can find it there. But so basically, this is just to show these gray ones are the well, PC, Portland cement, and alkali activated materials. Um, the pH range where they're active or where they're stable, and then compared to different silica-based cements. So there's magnesium silicate, hydrate-based cement, there's magnesium carbonates, magnesium phosphate cements, and magnesium oxychloride or magnesium oxysulfate cements. So those are, let's look into in more detail into those. But first, a little bit about the difference between magnesium and calcium. So as has become clear, this is the one of the major things here. What's going on is that the current binder, the current cement is based on calcium silicates, and so the option would be then to move on to less carbon emissions producing magnesium-based systems. And so what is the chemistry difference there? So the chemistry is quite similar in the sense that their magnesium and calcium are next to each other in the periodic table. So they behave quite similarly, but there are some differences as well. But they have the same charge. They're roughly as abundantly available. But then there is some questions that have been asked. So the global availability, actually 5 years ago, even 3 years ago, this was still a big question in the industry. That was the biggest sort of reason why big companies are not looking into that, is they cited the availability issues of magnesium. But since then, it has become clear that those are actually globally available. They just haven't been mapped as well as calcium. So they are available, and in large enough quantities, we could store all the cement, all the CO2 emissions for the next 1,000 years in the magnesium silicates that are known. So there's no issue there. The cost of processing has been another issue. So this is a work that's been done in more in the carbon capture and storage literature. And there, the cost of processing has been a major issue. However, according to the new results, this is no longer an issue. We can actually separate the magnesia out of magnesium silicates, and it should not be an issue of cost. Another thing that has to be sort of definitely or more precisely mapped out is the durability of different phases. And so this is something that we know. We have been working with calcium silicate based cements for 150 years. So there's a lot of knowledge about those, and we're not there uh, yet in terms of all the magnesium based phases. And there are a lot of different phases. We'll look into that. Another thing is that the sort of hydration agents or different admixtures that have been developed for calcium-based systems, they don't actually necessarily work for the magnesium-based systems. So we're lacking this development for the admixtures and different additives that are needed in order to make the magnesium-based cements work better. I believe you can get a taste of this difference in terms of what is the performance of, or what was the performance of this current cement in, let's say, 20 years ago compared to now. And you can see that the development of admixtures has had a major change into the how concrete is poured nowadays. And so similarly, you could think that the development of magnesium-based admixtures could revolutionize also that field. Kinetics also in some specific binders is still, and that's also tied to the admixtures that we don't have these admixtures or hydration agents developed yet. Okay, so RM CO2 emissions, this refers to raw material related CO2 emissions. And so I guess this is just to repeat that for calcium oxide, in order to produce calcium oxide or calcium silicates, you will be producing as much CO2 by weight as calcium oxide. So that by volume, that's 1,000 times more CO2 than the end product. And with magnesium, you don't have this issue because you're starting from magnesium silicates and brines. And so basically, this is actually a mistake there. There shouldn't be a CO2 there. But if you do add the CO2 there, you can actually achieve negative CO2 negative emissions with this binder, or with the different binders. So in terms of abundance, calcium is available as calcium carbonates, but also in industrial side streams. And this is an important place to start. And this is where most of the work currently is headed also, is that, let's say, carbonation of, for example, construction or demolition waste is an important topic that's considered. So basically carbonation utilization. And magnesium is available in different non-carbonate sources. One thing to note is that magnesium oxide is currently listed as a critical mineral here in EU, and that's the reason there is basically a geopolitical dependence on individual country on the availability, and that's because we don't have big magnesite reserves that are pure enough. But I think this is a sort of technology related issue now that we have magnesium silicate processing technologies in order to derive magnesium oxide from that. I think that's a matter of time when that will be resolved, but that remains to be seen. In terms of the abundance, in the Earth's crust, there's about 5% calcium. This is by weight, and 3% magnesium oxide. And of course, magnesium is much lighter than calcium, so it is quite similar in terms of the volumetric availability, which is more important. The slags and ashes are mostly calcium based, so there's only small amounts of magnesium. So that's not so available in the waste materials. So now I would like to go a little bit more into the chemistries of the different binders, the different binder systems. So maybe I'll just list them here and then go more into detail. So MSH, magnesium silicate hydrate, is the first one. Then the second one is magnesium oxychloride or magnesium oxysulfate. Then we have magnesium phosphate. And maybe I'll just say it here that magnesium phosphate is actually, engineering wise, it's a really good binder in the sense that you can make a durable product, and it's really rapid to harden. It has a high performance in that sense. However, phosphate is a critical mineral, and so that would compete with the fertilizer feedstock, and so to me that's a non-advisable to go to that direction. And as you can see, there's a potential unintended consequence of not being able to produce enough food for the global population. So that's strongly advisable not to further develop these magnesium phosphate cements in large scale applications. So then we have magnesium carbonates systems. Sorry, this is magnesium carbonate without any crystal water. So this is magnesite. But magnesite is it needs high temperature and pressure in order to form, and it's a cubic mineral, so it has been deemed not to be a potential cement system. So instead, what we have is sort of HCB cement, hydrous carbonate containing brucite, um, and hydrated magnesium carbonate systems. And so these are the binders that we will look more into detail. Okay, so let's start with magnesium silicate hydrate. So this is similar, well, kind of similar to calcium silicate hydrate, which is the cement that we're all used to. We're just using magnesium instead of calcium, and it's a 2D lattice. And you can basically form it by mixing magnesium oxide and silicon. And the TRL is around 8 or 9, so it's used in different applications. It has a lower pH, so the rebar would need to be rethought in terms of the structural applications. The advantages there are that there's a carbon neutral feedstock of magnesium. It has a lower pH. It is highly durable in, for example, marine environments, and it does not carbonate. This is actually a very interesting result in that magnesium silicon um, bond is thermodynamically more stable than magnesium carbonate. So even if you expose it to carbonate environment, it does not, unlike CSH or the regular Portland cement, which carbonates and exposes to steel, does not carbonate. So that's an interesting advantage. The reason why I have the question mark there is that this is a new scientific result, and then it should be replicated in order to be sure on that. And this is some work that we have done. The challenges that are being battled here is that there's a higher water demand, so need for better admixtures, and there is no admixture development yet. We're also working on that. Compatibility, because of the pH, there's a compatibility issue with the current steel reinforcement. And then also I've listed here the MGO market and the recovery technologies, excuse me, that need to be further developed in order to be at the scale that's needed. So that's magnesium silicate hydride binders, and those are closest to the market of these magnesium binders. Then we have the two different magnesium carbonate binders. And here, maybe I'll just say that magnesite, which is the thermodynamically stable phase, is kinetically hindered, so that does not form cement. But then we have these two, which is the HCB and HMC, which we'll look more into detail. So first, HCB, hydrous carbonate containing brucite. This is also known as the so-called Novasem cement. There was a startup company called Novasem 15 years ago that first used this formulation, and they actually still have or there's still their old patent that will expire in, I think, 4 years. But basically what you do there is you mix magnesium oxide with some, let's say 10% of carbonate ions in different form, and that forms, this has been just past year, we have been able to elucidate what is that. So it forms a distorted brucite phase. That's why it's called hydrous carbonate containing brucite. And the most work on this has been done in EMPA, and they have a big project working on that, and the technology readiness level is around 5-ish, I would say. And so here, this is one of their papers by Frank Winnefeld and Alex German from earlier this year. And basically you have this ternary diagram where you have brucite and then just 10% of carbonate, and then you have this hypothetical phase that they're looking at. And yeah, maybe that's about it. So it is, maybe I'll just, this is the hypothesis that they're putting forward, and that we're also looking into, is that why is it distorted, the structure? And it seems like the carbonate group goes into the lattice and therefore distorts the structure. Um, but here, there's also these other minerals that are listed here, and these are actually the hydrated magnesium carbonates, which was the other binder. So let's look into those more. So for example, here nescoanite, you have, this is a mineral phase, which is magnesium carbonate, and then 3 water molecules. And so you can see the same nescoanite is here, here at the top right corner. And so what's been published in the literature are nescoanite and hydromagnesite phases that have been thought to take part in these cement magnesium oxide carbonation phases. And this is the most advanced work on this, I believe, has been done by Chise Unlua from Glasgow University. And what she's been doing is these what she calls reactive magnesium carbonate bricks, where you take magnesium oxide and then gravel basically and make bricks out of that. You make those porous enough that you can carbonate them in the atmospheric environment. And when you carbonate them, you end up with some kind of nescohonide hydromagnetite binder, which seems to be durable. Um, However, if you look at the thermodynamic stability of these phases, Nesco and hydromagnetite, so this is the thermodynamic or the Gibbs free energy basically, and what it means is that the and as a function of temperature, and what it means is that depending on the temperature, different phases become thermodynamically favored, which would mean that if you make, let's say, Nesco binder at 20 degrees and it's exposed to, let's say, minus 20 degrees, uh, in theory it could turn into nescohonite. So this is what it's suggesting. Of course, these could be kinetically hindered, so it does not mean, like for example, magnesite is predicted here, but we know that magnesite does not form in these temperatures. So it's not quite that straightforward, but this is what has been sort of discussed in the literature, and so that has to be sort of taken seriously, and then the durability has to be improved in order for these minerals to work as a functional binder. Um, as a functional cement, I should say, in the outdoor like exposure. But there is possible to use, I would say this would be some of the lowest hanging fruit in terms of technology utilization. I believe these kind of companies are already perhaps in the market, is that if you take this nescohonite and you dehydrate that, it actually functions similarly to gypsum. So you have this dry powder, which is dehydrated nescohonite, and when you add water to that, it hardens just like gypsum does, and it's volumetrically stable, and it actually has better water durability than gypsum. So if you know, for example, these gypsum boards, so this could be a way to make gypsum boards like that are carbon negative, and I think that that would be one of the fastest ways to get to the market when that would produce carbon negative products, and carbon negative products in the sense that are also scalable in terms of the global volumes. So that was my overview of the different binders, and also the sort of importance of the phases and the motivation. So with that, I'd like to thank you for your attention, and if you have any questions, I'd be happy to answer.
Thank you so much, sir, for being here and contributing to the success of our seminar. Now, I will be taking some questions from our viewers. So, the first question is, if magnesia based binders become a mainstream solution, how might this influence traditional industry related to cement and concrete? And what adaptations might be necessary?
Yes. So I believe this is asked from the sort of engineering point of view. So I would say first that comes to mind would be this reinforcement. So currently we use steel reinforcement, and that uh, has to be studied much more in order to make sure that we can make a durable reinforcement. So that's for sure um, one adaptation that's necessary.
Moving forward, I would love to hear your thoughts on how can students or aspiring researchers actively contribute to the development and understanding of magnesia-based binders in pursuit of more sustainable concrete solution?
Um, I think so. As far as researchers, that would be looking into the research questions that are posed in the literature. So, for example, the paper that was published that are alluded to by this RILEM TC and BC, just I believe a month ago. That poses the research sort of framework and or the research questions that are open. So I think those kind of papers are good in terms of looking at what are the research questions that are open, and basically just starting to study and collaborate on those issues. And I maybe I should stress here also that the um, the advantage of collaboration, so that we don't do duplicate work basically, and I think that's really important. And as especially in terms of these sort of new research areas such as magnesium cements.
Next question. In marine environments, how will the magnesium-based cement be able to tackle corrosion of reinforcement?
So this is an interesting question. There are uh, like I said in the talk, this is actually more durable cement in terms of the cement itself in the marine environments. I don't recall that there has been studies in terms of what the reinforcement does. There is in the ICC conference earlier this year, there was a very interesting talk by I forget who it was, but it was basically uh, saying that the pH may not or the pH is not the only thing that's affecting the durability of the reinforcements. So I believe there could be magnesium is very how would I say it, active towards chloride and sulfate. So perhaps there needs to be much more studies on this. But I believe that could there there's some surprising results also probably that's waiting for us there once we dig into that more deeply. So more
Thank you,
research
sir.
is needed there.
This brings us to the end of our session. I want to extend a heartfelt thank you. We are genuinely grateful for the time and effort you have dedicated to being with us. Now, I would like to invite the content head of the club for a vote of thanks.
You're muted.
Yes, sorry, sir. What a lovely session. I, Aditya Chandra, content head of our club, would like to express my heartfelt thank to our guest, Professor Paivo Kinnunen, and the club's faculty advisor, Professor Subhajit Mandal sir, on behalf of the entire SEST family. I'm very sure we all understood every question you responded enthusiastically. Also, many thanks to our lovely and patient audience. I hope we all learned a lot. Finally, I'd like to thank our great organizing team for all of their hard work in making this session a success. Thank you.
Thank you very much, Aditya, and thank you very much, Priya, and thank you everybody for who's watching. Thank you so much. Bye
Thank you,
bye.
sir. Bye, sir.